So Christian Latge is directeur de recherche at CEA. He's had a long career already. He was the director of the MEGAPIE project when it was an international cooperation between many different labs. And apart from being technically competent, he's also very diplomatic. So that was very important because we had a vast number of very different cooperating institutes who had to work together from all far corners of the globe. And these cooperating institutes managed, in the end, to get MEGAPIE to work, which was the world's first liquid metal neutron source operating at a power level of approximately 1 megawatt. So,
thank you, Chairman. Thank you, Karen. Okay, so I am going to present you some feedback of the project, MEGAPIE project, which is a work in partnership with 9 partners, NEA, PSI in Villingen, CEA, CNRS, SCK-CEN in Belgium, KIT, Europe for some projects to support our project, GEA and the KRE. So first I have to say that we managed the project with Michael, who has given just the previous talk. In PSI, he is particularly in charge of all the and very heavy things dealing with operation and then with the decommissioning, waste management, and preparation of PIE. And here you have a list of partners, but we have not all the partners because we have many participants to this project coming from the all organizations. So MEGAPIE was decided in 1998, end of 1998, by 3 persons, Mr. Heusner, Mr. Günther Bauer, and Mr. Massimo Salvatores from CEA. So this project called MEGAPIE, it means the 1 megawatt target, megawatt pilot experiment, was initiated in 1999 in order to design and build a liquid lead bismuth spallation target, and then to operate in Villingen with a ThEC13 facility. So one of the main constraints was effectively to design a quite different target inside the same geometry as the previous, you have seen previously, as described by Michael. So it was equipped with, of course, a lot of instrumentation, we will see later. And there are several main challenges of this project. Of course, to design a completely different concept of target in the same geometry, to develop and integrate 2 main prototypical systems, specific heat removal system and electromagnetic pump systems, to design a 9 chromium martensitic steel T91 beam window, to license this target with LBE in relevant conditions, a liquid target, and to operate this target, of course, to develop the decommissioning strategy and waste management, and of course, at the end, to characterize the LBE and the structural material. So just to describe the target, it's about 4.5 meters height. There is 2 parts. Here, there is about 40 centimeters diameter, and here 20 centimeters diameter, more or less. It was operated between 230, 40 degrees for the cold temperature, up to 330, according to the design. We have a circulation of the lead bismuth going to the window here, just in front of the proton beam, and then the LBE is moving in this direction, going thanks to pumps to the exchangers cooled by oil. Then the LBE is sent back to the bottom. In order to avoid a static point here and a hot point, we have a bypass line with a second electromagnetic pump, which drives the LBE and perturbates the flow here in order to avoid any hot point. So there are the design parameters here. You can see here the total conditions. The design pressure is 16 bars. Design temperature 400 degrees Celsius. Cover gas pressure 3.2 bars. Operation was estimated to be 1 year, but we will see later that there was a study in order to establish which could be the maximum duration of operation in order to avoid any crack due to, for example, the drift of the DBTT. Okay. And the amount of LBE is 89 liters. And the weight, total weight is 1.5 tons. Okay, so here is just an illustration. It is a multidisciplinary project, okay, where we had at the beginning the necessity to define what would be this target, because it was really a first of a kind of this target. So, of course, we need a material specialist, physical chemistry, particularly coolant chemistry, thermohydraulics, mechanics, and neutronics, of course. So, yeah, there are a lot of data to collect. Then there was a lot of analytical experiments in order to support the design, research directly in support to the project, or some others which were performed in some European projects like ThEC13, like and some others. So, and after that, there was also some validation and mock-ups of some parts. After that, there was several main steps: the manufacturing of the target, the integral test, the operation, the decommissioning and dismantling, the waste management, and of course, during the dismantling, preparation of the PAE. After the operation, of course, analysis of the results we have obtained, and integral tests were dedicated mainly to licensing, because we have, of course, to report, and particularly PSI, to report to the Swiss safety authorities. Okay, so the main steps, okay, is a long project, but it is a project from A to Z. It means that it is, we are very lucky to participate to this project, because we have the from the design to the PAE. So the feasibility studies, the main requirements were defined in 1999. Then feasibility study 2000, design studies 2001 to 2004, design support 2001 to 2005, manufacturing of target, but also all the ancillary systems, because we need to develop a lot of ancillary systems, particularly for cooling and for insulation and so on. Integral test between September to December 2005, transfer to ThEC between January and May 2006, irradiation during 4 months exactly, between mid of August to around mid of August to 21 of December 2006. Then post-test analysis, it means analysis of the results we have obtained in thermohydraulics, in neutronics, and so on. Decommissioning, very long operation, very long. Sampling for PAE, also a huge work. PAE, which is going on now since maybe 3-4 months. And now we are closing the project normally by end of 2014, assuming that we have obtained all the results. And of course, close to that, the waste management too. Okay, the choice of LBE, maybe I will not spend too much time on that, but it's clear that has been selected because it has attractive neutronic and physical properties with regard to the application for spallation. Good heat transfer coefficient. A liquid metal is very interesting for cooling the system, nuclear systems. And also we have a low melting point. So it's quite interesting to have this melting point at about 125 degrees Celsius. Okay, about the feedback from basic studies. We have a lot of basic studies close to the project in order to support the design and the studies. And the reason for the choice of T91, just to recall, it was higher strength, much better resistance to heat deposit, better corrosion resistance in Latge due to low nickel content. And there was a lot of material studies focused on MEGAPIE and also more generally performed within the frame of Eurotrans project, for example. There are many studies related to oxygen control, oxygen measurement with electrochemical oxygen meter, studies on corrosion, mechanical lead bismuth freezing and consequences of this expansion, for example, thermal expansion during the freezing of the LBE after the operation in order to prevent any embrittlement of the target and any damages in order to perturbate the results of the PAE and so on. The lead bismuth water interaction also, and so on. So we had a lot of experiments to perform. Okay, just an example here is we have investigated the freezing operation. We have seen that there is an effect of the cooling rate, and this is thanks to some experiments which were performed in Enea in Brasimone. We have done some. We have prepared a procedure in order to cool down the target. This is an illustration of some R&D which is necessary for the project. Okay, the feedback from the manufacturing. So the manufacturing of the target itself was done in Nantes, so in Brittany, by a ThEC company. And so they prepared this very complex target, okay, in terms of geometry, because the designer they have no problems for the manufacturing, but after that you have to do the job. So they had to work on the joining and welding procedures qualified for various configurations, and so on. So there was a heavy work in this during this phase. Here you can see some components. Here you can see the window. Here the inner pipe with a bypass pipe, which distributes the lead bismuth. Here, this target head, which was provided by PSI. Here you have the heat exchanger, which was designed by CEA and developed installed by ThEC. And also, you have the pumps, which were developed by Institute of Physics of the University of Latvia. The main ancillary systems were developed mostly in Italy and also in Swiss, and for some others, particularly for the decommissioning in Germany. It's typically the case for the sauce for decommissioning by Beringer company, for example. Okay, the feedback from integral test, I don't go into much detail, but there was a very important step before to install the target in front of the proton beam. It was tested in the real conditions with devoted heater at the bottom in order to see different points. Of course, to establish the procedures for LBE filling and draining operations, checking the operability of main components of the target, check and calibrate the instrumentation, determine the thermohydraulics characteristics of the system, simulate heat deposition with the heater, obtain the vital parameters for system control. This is very important because we know that we anticipate the fact that there was some trips, and it was necessary to check that the control system were able to mitigate the effect of this phenomena. To provide enough information for licensing the target for irradiation test. There was a huge work done by a PSI for the licensing, because in fact the responsible of the operation was PSI, and there was to provide a lot of information to HSK and also to NAGRA after that for the waste. Okay, and already also some information for model verification, and particularly the system code. We use the RELAP 5 for this purpose. Okay, about the feedback during this operation, generally we had a very good performance of the pumps. We have less success maybe with the instrumentation, particularly flow meters, we faced some difficulties of integration, but nevertheless, it was possible to monitor the flow rate thanks to particularly to improve the reliability of the measurements thanks to thermal balances, for example. Okay. Here it's an example of experimentally calculated temperature for an unprotected trip. You can see here the behavior of the target with measurements here and the calculations with RELAB 5. And you can see that the system is able to mitigate very quickly a trip. About the design of the target, of the heat exchanger, there was some calculations. It was probably oversized, slightly oversized. It means that there was a necessity maybe to re-examine the correlation we used for this purpose. There was a test. It was requested to have a test also in order to check what would be the behavior of the target in case of leak at the window. So this so-called full-scale leak test was performed in a very short time in PSI in order to check and to provide some information to the safety authorities, and particularly also to test the leak, LBE leak, to detect this leak with a device based on AC impedance, which was developed by PSI also. Okay, so the irradiation, I think that there was a presentation, so I will not insist too much, but the duration was about, so it starts the 14th of August 2006, and then it was operated at, I would say, full power up to December 21 or 22 of December. So there was a lot of instrumentation, but what we have seen that it's necessary really to have a good assessment of the instrumentation we need. Instrumentation for safety, instrumentation for operation, instrumentation to gather information for the validation of models, for example. So we obtained good results. So there was we had quite well determination of the flux. It was said already, but it was the flux of neutrons was about 80% over than the flux obtained with solid targets. We faced, of course, some trips. There was a lot of trips, but of very short time, and thanks to the control systems, we have not obtained very important damages, significant damages due to this period. But nevertheless, we are waiting for the PIE to confirm this status. About there was analysis also of the radionuclides present in the gas. We have a good agreement with the previous calculations because the team in charge of neutronics had to have a prediction of the contamination of the gas, which was produced by the irradiation. Okay, I moved to the decommissioning phase. So after that, the target was remained in position. And then during this decommissioning, so the target was extracted from here, then put in a special container and transferred from east side to the west side to the SVILAG hot laboratories. During this decommissioning phase, it was necessary to cut the target with a very special tool developed by Behringer company. It was cut in 19 slices, and then some samples were extracted for the PIE. I don't go into much detail. What we have observed, nevertheless, in the bottom of the safe hull is that there was some leak. Probably we estimate that maybe there was some leak of oil. There was an explanation in this space, and which produced a little amount of carbon products in the bottom. There was also an in-service inspection of this target in order to check if the thickness has been modified by the operation. And what we have seen is that there was no detectable change in the thickness of the window. So the technique was very efficient in order to check the thickness of the window. About the PIE, so about the PIE, of course, the objective is to understand the microstructural, mechanical, and chemical changes in the structural materials in the target induced by irradiation and maybe LBE corrosion. And after that, also to characterize the LBE coolant. Here you can see an EDM cutting machine. Here you can see on a sample on the window, some samples on a dummy target. Of course, we prepare the sampling. And then we have performed this, we have started to examine these samples after transportation and after draining the LBE, cleaning with regard the alpha contamination particularly, and also preparation of the transport itself. Okay, so okay, here you can see a mapping of the samples. Okay, there was about more than, on this window of 20 centimeters, there was about 700 samples, if I remember well. Okay, so there was a round-robin test in order to prepare the laboratories to have common approaches for the characterization. After that, on the samples, before to prepare the samples, there was a segregation of LBE. There was an oven to melt the LBE. And then you can see here a slice before and after melting. Cleaning and decontamination, there are the two main solutions we were investigated, and there was a decision to use the nitric acid for the final cleaning of LBE after comparison with another solution. So the cleaning operation were also qualified for this purpose. Transport of the PIE samples, they were transported in Belgium, France, Germany, Japan in Tokai, and USA. It was last April and beginning of May. And of course, some samples remains to PSI. No transportation, but okay, irradiation. But in order to analyze the samples, what we need is effectively to have a good mapping of the irradiation parameters, of course, such as irradiation dose, helium and hydrogen production, proton and neutron influence, irradiation temperature, and temperature itself. So there was we make some calculations of the proton fluence distribution, and there was some measurements also after that, and so there was so the proton fluence distribution was established from the measured data, and what we have observed is the maximum proton fluence of the MEGAPIE target at this value, 1.93 10 to the power 25 protons per square meter. Another aspect important for this is also to have a good mapping of the temperature. So there was some measurements with the thermocouples, but also there was some large eddy simulations code in order to study the instabilities, and particularly induced by the bypass tube. So there was a good characterization of the temperature, but sometimes we have noticed that there was some temperature measured about 15 degrees higher than predicted. So there was some discrepancies, and we have observed also which was predicted, a difference of temperature between the inner side on the LBE, on the side of LBE, and the other side. Study of instabilities, okay, I told that with large eddy simulations, which is very important to know the stresses on the structures. All these things are tools to analyze after that the PIE. About the chemical and radiochemical analysis of LBE, I don't go into much detail, but there was very important work performed essentially in PSI. But we have some predictions, and particularly we have tried to have a qualification with some experiment which was performed here in the CERN, in the Isolde facility, on LBE, irradiation of LBE, in order to establish and to predict what would be the production of radionuclides. About results on LBE samples, of course, there was a lot of products, and particularly, so there was particularly results on bismuth, on gold, on lutetium, distribution in the MEGAPIE target. For some of these nuclides, the activity can be easily evaluated from gamma spectrometry results, while other nuclides can only be determined after chemical separation. So it was a complex and log activity in hot laboratories. And it was a good opportunity to give some work to PhD students also. Okay, so about the LBE, the bismuth, it was clear that the bismuth was also remained mainly in the LBE. Sometimes there is a question and saying, what about, bismuth, polonium? And they say that sometimes polonium can be an issue. What we have seen and we have confirmed during operation is that polonium mainly remains in the LBE bulk. There were some studies also close to this MEGAPIE. For example, extraction of this radionuclides from the LBE, and there were some studies performed at PSI, particularly based in partnership with the University of Bern. This is one example of the collaboration, but I would like to say that thanks to MEGAPIE during long years, there was a lot of universities which were involved in these activities. Okay, as a conclusion, I would like to say that, of course, this target was designed by a MEGAPIE consortium manufactured in France, Latvia, and Switzerland, and Italy and Switzerland for ancillary systems. The target operability was demonstrated. It was a first-of-kind experiment. The irradiation was carried out in 2006. It seems a long time before. But what this also shows is that the time after that to prepare, to dismantle, decommissioning, and analyze and prepare the sampling is very long. Decommissioning and waste management phase were defined and executed properly by PSI. Post-irradiation examination were prepared by MEGAPIE consortium, cutting, sampling, and so on. Chemical analysis also was performed. So as a second conclusion, I would say that the MEGAPIE project feedback provides to ADS community, of course, unique and relevant design, but also operational feedback. And there is a feedback on materials, on the materials, on coolant behavior, on physics, on thermohydraulics, and so on. It's a huge feedback for ADS community, but not only for this community, because this is a characteristic of this project. It was a meeting of 3 different communities, I would say. ADS community, the community of fast reactors also, particularly for lead and LBE, but also in some aspects for sodium. I can detail if you ask me, but we have investigation about the possibility to use LBE as a coolant for intermediate loops in the sodium reactor, for example, or for some other things. Material behavior also is of interest for all the communities. And finally, for neutron scattering community, as it was explained previously by Michael. So I would like to thank particularly the 9 members of MEGAPIE consortium, all contributors to the MEGAPIE project, and more particularly the PSI team for its constant dedication for the operation particularly and for the last phase, but not only. The European Commission who support us during different projects. And I would like to thank you for your kind attention.
Right, so we'll have some questions either to Christian regarding MEGAPIE or...
And Michael also.
Yes.
How much would it cost if somebody wanted to ask you to provide a 1 megawatt source, like MEGAPIE, maybe implementing whatever you have learned in this first step? What is the cost estimate of this project? Of this target, yeah. I'm not talking about the beamline, just the target. I mean,
I know. The target, I think that the cost of investment, you know, it's about 2 million.
I would say 2, maybe 5 million for the target itself, for the hardware, without manpower, of course.
We probably prepare a balance. Next October, we will have a final review of the project. And probably we will have a lot of balance in terms of cost and so on.
Right, the gentleman here, I think.
My name's Ed File. I was wondering if anyone did any evaluations as to what the burn-up density as a function of radius from the beamline was, and was that going to be controlling on when you had to refuel the reactor, i.e. the stuff next to the beamline in the reactor was going to burn out long before the stuff at the larger radius from the beamline?
I'm not sure to have
this would be in an ADS, right? We're only talking about a spallation source here.
Right, I'm talking about this installation of this in a reactor scenario.
Mm-hmm.
So what was inserted actually in the target, in the central rod, there was a central rod, there were several foils of neptunium, americium, etc. inserted there, which were then at a later stage analyzed by CEA, as far as I understand.
And provided by CEA,
and
fission chambers.
This is available in some publications data.
But if your question is related to the control of the proton, how to this is the right answer, or?
The question is, will the fuel next to the beamline, where most of the neutrons are created, going to burn up the fuel that's right adjacent to it and not burn up the fuel that's at a large radius from the beamline in the reactor? Such that you have to refuel based on burn up next to the beamline and not far from the beamline.
Right, I think the gentleman is assuming we put this neutron source inside a subcritical core, and he's asking a question regarding the
implementation in a reactor.
Yes. I don't know if maybe Hamid wants to comment, or
The question is, for sure, depending on the geometry of your spallation source in regard to the fuel that you are having around. A target like the MEGAPIE is the one today we are envisaging within mirror in terms of dimension, and the flux tilt, the radial flux tilt, in the adjacent fuel assemblies as compared to the most outside fuel assemblies is about 20% only. So you are not burning that much close to the target as compared to the outside fuel assemblies, and that depends for sure about the source importance you have. So,
right. And we have another view from Jean-Pierre Revol, who...
Just an additional comment. This morning I showed to you the importance of it's not only the target, it's the system, as Amit said, and I explained to you that K infinity has to be chosen properly to minimize the thing. If you take K infinity less than 1, you have an exponential decay of your flux, and then you're very non-uniform in the burn-up. So you have to adjust the whole geometry of the system and choose the proper parameters for K infinity, for instance, to minimize the...
There's a gentleman at the back waiting for
I would like to ask you or Michael, how do you determine the length of the target, and how do you handle the single diffractive protons?
Sorry, I did not quite understand.
How do you determine the length of the target?
The length?
Yes. So, I mean, what are the conditions that determine the length? Like how long the proton will travel?
Okay, I see. Of course, this is, as you might have seen in our D2O moderator tank has a radius of 1 meter, in forward direction, of course, we have to have quite a lot of shielding because we have high energy neutrons in the forward direction. So that's what we have to shield for. So the upper part is certainly determined by the shielding necessity that we have up to a certain point, and the lower part simply has to be in an optimum position to serve our deuterium source.
So it is something like the range of 600 MeV proton, say.
It's roughly 2 meters, 3 meters of shielding in the upper part, iron shielding. Okay. And then on top of that, there's a room, and on top of that you still have a lot of shielding, concrete shielding again.
Okay, thank you.